All right, so in this example, we're going to look at stretches and shrinks for horizontal transformations. Well, at this point, hopefully you recognize the fact that we are affecting the input here. So this is going to be a horizontal transformation. P of x is normally equal to x squared. So if I want to get that 3x squared, I'm going to need to plug in a 3x. So in other words, this piece right here is the same as P of 3x. So what that means is I'm going to hit my values faster. F of 0 is just equal to P of 3 times 0, or just P of 0. And so in this case, there's no change. When I plug in 0, I'm just going to get 0. If I look at another example, F of, let's say, 1, now we're going to start to see a change. So F of 1 is going to be equal to P of 3 times 1, which is then, of course, just equal to P of 3. So when I plug in a 1, I need to jump down to P of 3 and use that value. So if I continue that and look at F of 2, well, that tells me that when I want F of 2, I need to go to P of 6, and that tells me that 36 will be my output. So in other words, if you notice, we're just skipping ahead faster and faster and faster. So what's happening here? Well, I'm going to, my values are clearly increasing much faster than they used to. So I'm going over 1 up, over 1 up 9, and then the next one's going to be over 2 and up 36. I can't even graph that. It'll be up there somewhere, right? So knowing that there is some symmetry here, and you can plug in some values to check my work, what we're going to see is that our graph is going to look squeezed. Now, it might seem more like it's stretched. However, since this is a horizontal transformation, what's really happening is we are shrinking horizontally. So the way I would think about it is we have to travel less far than we normally would to increase vertically. Again, this can be kind of a difficult concept to think of, but the easiest way to identify this is to kind of compartmentalize it. First off, we identify the fact that since it's happening inside that square function, we know it's a horizontal transformation. And then just remembering that our values are going to get bigger faster, or they're going to cycle through faster. Well, that's telling us we're going to get skinnier, which looks like a shrink if we're thinking about it horizontally. Well, what if instead we had something like this? Well, if in this case we were going 3 times as fast, in this case we're going half the speed. So looking at a few values here, first off, let's go ahead and agree that for g of x, if I plug in a 0, I'm going to get a 0, right? So that part's not going to change. I'm going to have that same value here. However, if I were to plug in a 1, I'm going to get a much smaller value. So I'm going to be a little strategic here. I'm going to go ahead and put in a 2. So now when I put in a 2, I really just get a 1. So you can see here that my values, I'm getting to them slower. So hopefully you can guess the next value I would choose would be to put in 4. And when I plug in a 4, I get a 4. Again, I'm going half the speed. So it normally only took me until I got to 2 to get that 4 output. But now it's taking me all the way until I get to 4. And so I can plot those points. And again, hopefully you're starting to see some of the symmetry here. I'm not going to go in depth with it yet. But what we're going to see is that if I go, or if I look at the next point, 2, 1, and then the point after that is 4, 4, and then kind of mirror those across the y-axis, what we see is that it seems like we're going up slower, but the way we should think about it, since we're thinking horizontally here, is that we're actually stretching our graph out horizontally. So in this case, we would call this a horizontal stretch, as opposed to our previous case, which was a horizontal shrink. Now, see if you can come up with a more formal way of defining this as to when we can identify a horizontal shrink versus a horizontal stretch.